chemistry, we're moving on to the next lesson in the Foundations unit, and it's on something called the octet rule. So the 90 natural elements on the periodic table combine to form millions and possibly even billions of compounds. Chemical bonds are central to chemistry because they are how atoms are joined to create these new compounds. Even so, there are only three ways that elements combine. The first is ionic bonds, and that's when an atom passes electrons to another atom. That takes place between metals and nonmetals. Next are covalent bonds. That's when atoms share electrons, and these take place between two or more nonmetals. And finally, there are metallic bonds. Electrons jump from atom to atom like frogs on lily pads. We'll talk about metallic bonds in a later unit and when we deal with specifically with metals. So first we're going to talk about the octet rule because it's central to chemical bonding. The octet rule says that atoms are in the most energetically favorable state, and sometimes we use the metaphor happy. They're happy when they can fill their valence orbital. Octet means 8. It refers to the number 8. It's called octet because all elements except hydrogen and helium, the first two on the periodic table, need 8 electrons to fill their valence or outer orbital. Hydrogen and helium, their first orbital can only hold 2 electrons and then it's filled. It's still called the octet rule, however. Octet rule really means that atoms want to fill their valence orbital. So, noble gases such as helium and neon at the end of each row already have full valence orbitals. So if you look at helium, it has 1 orbital. The first orbital can hold 2 electrons, and that's what helium has. It has 2 electrons in that first orbital, so it's filled. It can't fit any more electrons in that first orbital. That means the next electron would have to go into a second orbital. If you look at neon right below helium, it's also a noble gas on the far right-hand side of the periodic table. You will see that when you draw the diagram of it, it has, it has 8 electrons in its outer orbital. And all atoms from the second row on down want to have 8 electrons in their outer or valence orbital. So that orbital cannot fit any more electrons. That means if you want to add an electron, you're going to have to create a third orbital and go down to the next row on the periodic table. But the point is that all atoms want to have this full valence orbital structure like these two atoms. So they're called noble because they're like royalty. Other elements want to be like them. They want to either add or lose electrons so that they have a full outer orbital. Now the reason for that, the deeper reason for that, is just what it says above. It's more energetically favorable. You don't really have to understand the explanation any more than that. It's just kind of one of the miracles of nature, and this is just the way nature made atoms. So all atoms want to be like a noble gas and have a full valence orbital. Now lithium, if you look at its structure, we've dealt with lithium quite a bit so far. It could gain 7 electrons. So there's lithium, and you see it in the red box on the periodic table. So it could gain 7 electrons to be like neon way over there on the right. Well, the problem is lithium has a very low electronegativity. We've already studied about that, and it is not going to gain even 1 electron, let alone 7. So that's never going to happen. Lithium is never going to fill its second orbital by adding 7 electrons so that it has a total of 8. But there's kind of a backdoor way that it does it. Or here's what lithium can do. It can lose its second orbital electron, that 1 valence electron, and have a full first orbital like helium. So in other words, instead of going forwards toward neon, it can go backwards to helium by losing 1 electron. Since lithium has a low ionization energy, that means it very easily can have that electron pulled away from it. We learned about that. Over on the left side are low ionization energies, so they easily lose electrons, and lithium easily loses that valence electron, that second orbital electron. And there it goes, so it's gone. It got pulled away by some other atom. So conclusion, the easiest way for lithium to be like a noble gas is to lose one electron and have a full first orbital, like helium. Lithium will never gain 7 electrons, but it will very easily lose an electron, so now it has a full valence orbital. Its valence orbital is now its first orbital. When lithium loses an electron, it becomes a cation. That's a positively charged ion, and is called an Li1+ ion because it has one more proton than electron. When lithium has 2 valence electrons in its first orbital, it is said to be isoelectronic with helium, meaning it has the same electron structure as helium. So one orbital with 2 electrons is the same as helium. But lithium does not turn into a helium atom because lithium still has 3 protons to 2 for helium, and it's the protons that define the identity of an element. So all atoms want to be like a noble gas and have a full valence orbital. Fluorine has an easier way. The nearest noble gas is neon, right next door. So you see where fluorine is and you see where neon is. So fluorine can have a full second orbital simply by picking up 1 electron. And we know fluorine can do this because it has a high electronegativity. And that means it easily pulls in electrons from outside of itself. So it can easily gain that electron. So there you see the electron just came in, and now fluorine has a full valence orbital, a full outer orbital. So, and it's referred to as an F1- because it has one more electron than proton. You can count them there. So conclusion, fluorine gains 1 electron to give it a full second valence orbital with 8 electrons. Fluorine becomes isoelectronic with neon and is called F1-. Alkali metals, which are on the far left column with the exception of hydrogen, that's lithium, sodium, potassium. Alkaline earth metals, that's the second column, beryllium, Be, Mg, magnesium, Ca, calcium. Or transition metals, and boron is a metalloid, have low ionization energies and more easily give up electrons. So that's everything that you see in green. Metals, which become cations, positively charged ions, are shown in green below. Nonmetals have high electronegativities, so they can gain electrons. Nonmetals can most easily complete a valence orbital octet by adding electrons. So nonmetals, which become anions, negatively charged ions, are shown in blue below. The nonmetals in red do not easily either gain or lose electrons, and they do not ionize. Noble gases already have full octets, as we just saw, and do not gain or lose electrons. They're happy. They just want to be just the way they are. They're fine. Now we're going to take a deep look at the second row elements, and we're going to see how they ionize. And the way that the second row elements ionize is the same as the way all the other rows down below. Now we're only looking at the representative elements. Those are the first 2 columns, alkali, alkaline earth, and the last 6 columns on the periodic table. Those are mostly the nonmetals over there, although down lower there are metals. So let's take a look at this. So how can lithium have a full octet, a full valence orbital? And we just talked about this. Lithium can have a complete octet by filling its second orbital. This would require adding 7 electrons. Since lithium has low electronegativity, that is the ability to pull in electrons, this would be impossible. So lithium will never do this. It will never gain 7 electrons. Instead, it's easier for lithium to give up its 1 second orbital electron as well as the second orbital. This means that lithium would have a filled first orbital, the same as helium. So we saw this example earlier. So there goes the second orbital electron in the second orbital. So lithium loses 1 electron, giving it a 1+ charge. Now beryllium. Beryllium can have a complete octet by filling its second orbital. This would require adding 6 electrons because it already has 2. Since beryllium has a low electronegativity, this would be impossible. So beryllium will never gain 6 electrons. It's never going to do this. Instead, it's easier for beryllium to give up its 2 second orbital electrons as well as the second orbital. This means that beryllium would fill the first orbital the same as helium. So there, it's also isoelectronic with helium. 2 electrons in the first orbital. So beryllium loses 2 electrons, giving it a 2+ charge. Boron. Boron can have a complete octet by filling its second orbital. This would require adding 5 electrons. Since boron has a low electronegativity, this would be impossible. So boron will never gain 5 electrons. Instead, it's easier for boron to give up its 3 second orbital electrons as well as the second orbital. This means boron would have a filled first orbital the same as helium. So boron loses 3 electrons, giving it a 3+ charge. And again, you can see it's isoelectronic to helium. It has the same electron structure. Carbon can fill an orbital by gaining 4 electrons or losing 4 electrons. Generally, though, carbon does not ionize. Now we're going over to the right side, more to the right side of the second row. So nitrogen. Nitrogen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require nitrogen to lose 5 electrons. You can see it has 5 electrons in the second orbital, so that it has a full first orbital identical to helium. But nitrogen will never do this. It is easier for nitrogen, now that we're getting over to the right side of the periodic table, it's easier for nitrogen to add 3 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So there you see nitrogen now looks exactly like neon. It does not become neon because it does not have the same number of protons. But the electron configuration, it's isoelectronic with neon. So nitrogen gains 3 electrons, giving it a 3- charge. Again, gaining electrons, it becomes a minus because electrons are negative. They're negatively charged. Oxygen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require oxygen to lose 6 electrons so that it has a full first orbital identical to helium. Oxygen will never lose 6 electrons. Instead, it is easier for oxygen to add 2 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So there you see oxygen, and it's going to add 2 electrons there. Oxygen gains 2 electrons, giving it a 2- charge. Fluorine, same thing. Fluorine can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require fluorine to lose 7 electrons, so it has a full first orbital identical to helium. But fluorine has an extremely high ionization energy, so it's never going to lose 7 electrons. It's never even going to lose 1, really. So fluorine will never lose 7 electrons. Instead, it's easier for fluorine to add 1 electron, giving it a filled second orbital. This creates the electron configuration of neon. So fluorine gains 1 electron, giving it a 1- charge. This table shows the charge on the ion created by each element. You have a copy of this in your reference sheet section. Now, if you look at the first 2 columns, and the last 6 columns, those are the representative elements, and that's what we just learned. We just learned that everything in that first column, lithium, sodium, potassium on down, Li-Na-K, will lose an electron to be like the noble gas in the row before it. So lithium will become like helium, sodium will become like neon, potassium, which is K, will become like argon. They'll lose an electron to be like the noble gas before them. Same is true with beryllium, magnesium, calcium. They'll lose 2 electrons. Same thing. They'll go backwards to be like the noble gas in the row before them. Now, if you get over to the right side of the periodic table, you see that boron and aluminum do the same thing. They lose electrons. They lose 3 electrons. So boron will lose 3 electrons to be like helium in the row before it. Aluminum will lose 3 electrons to be like neon in the row before it, and so forth. Now, we said carbon and those in that column, carbon, silicon, germanium, don't gain or lose electrons. Now we go past that and we see that nitrogen will gain 3 electrons to be like neon. Phosphorus, P, will gain 3 electrons to be like argon. Arsenic, As, will gain 3 electrons to be like krypton, and so forth. Next column over, oxygen gains 2 electrons. Sulfur, S, gains 2 electrons. Selenium, Se, gains 2 electrons to be like the nearest noble gas. And then finally the halogens, which is the second to last column. That's fluorine, chlorine, bromine, iodine. They each gain 1 electron to be like their nearest noble gas. Now, if you look at the transition metals in the middle, you can't figure out their charge the way we just did with the first 2 columns and the last 6 columns. That's why you need this sheet. So we'll look at some of the different transition metals. That's the valley in the middle of the periodic table. So look at iron. Iron can lose either 2 or 3 electrons, giving it a 2+ or 3+ charge. Now, how do you know which it is? It just has to do with the context of the problem. It's usually given to you, but you can't figure out the 2+ and 3+ the way we did the others. It's just something that you have to be given. Copper can either lose 1 or 2 electrons, giving it a 1+ or 2+ charge. Tin, which has the abbreviation SN, can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. And lead can either lose 2 or 4 electrons, giving it a 2+ or 4+ charge. Now, this is another sheet that you have in your packet. It's called the 60 Common Ions. It's broken into 4 sections. The top section is the most basic. It basically tells you the charges that we just talked about. So sodium Na has a +1, chlorine has a -1, sulfur S has a 2-, and so forth. And then down below in the second group you see there, you have the transition metals we just talked about and the different charges they can have. There's a couple of more sections, and we'll go over that in class. It's called the 60 Common Ions in your packet. All right, and that takes care of our lesson on the octet rule and how charges are formed. This is going to be very important in understanding how chemical bonds work.